Right, so here's a problem we're going to look at. There's a diagram, and we're going to say, what are the tensions in the two cables if the system is in equilibrium? So that's the information we've got. So the first thing, we just draw a force diagram, free body diagram. So what's that going to look like? We're going to have the weight acting down, and then we've got the tensions in the two cables. Call that tension 1 and tension 2. And do we know we sort of know some angles? We can sort of put that that's 70 degrees. And that's 30 degrees. Okay, and now what's our force acting down? 10G is 98.1 newtons, because it's 10 times 9.81. Okay, so there's our diagram, and we might look at it resolving as well. You'll see your simultaneous equations and why sometimes it's quicker or easier not to resolve horizontally and vertically, but to do it by a triangle of forces. Okay, so now, because it's in equilibrium, we're going to get a closed triangle of forces. So there's our free body diagram. Let's do our triangle of forces. So the easiest one to start with, remember it doesn't matter which one you start, we just put them nose to tail, but the easiest one to start with is our weight acting down. So there's our weight acting down, so we've got 98.1 newtons there. And then I can have TA going up like that, or T1, and then T2 closing it off. Now, what angles can I put in there? What's this angle in here going to be? Or that one there? Which ones can we put in? Yep, one of them's 60, so this one up here is 60. And that one down there is 20. Yeah. Okay, so there's our triangle of forces. Okay. You think about why that is. With that angle there is 70, so if I draw across there, that's 70 in a right angle triangle, that has to be 20. Yeah? You got that, Nick? Yeah? If I draw a line across here to there, that angle there is 70, so that one must be 20. And if that angle there is 30, that one has to be 60. No? So let's have a look here. We can actually work out the third angle. What's the third angle? If one's 20 and one's 60, what's the other one got to be? 100, yep, so that has to be 100 degrees. So now we've got a choice of using sine rule or cosine rule to work out the different ones. But sine rule is easier than cosine rule, so let's use it. Okay, so if we use the sine rule, to find T1 first. So we always start with what we want. So we're trying to find T1. So T1 divided by the sine of the angle opposite. So opposite T1 is 60 degrees. So T1 over sine 60 degrees equals the force we know, 98.1, divided by the sine of the angle opposite, which is 100 degrees, the sine of 100 degrees. And we want to rearrange this. This sine 60 can come up to the top there. So T1 is 98.1 sine 60 degrees divided by sine 100 degrees, which we'll do on our calculator. Yep. So I've given this to 3 significant figures, so I'll give that. So we get 86.3. Yeah, what you said, Levi. Okay, and then we use the sine rule again just for T2. So we can say, I'm trying to find T2. The angle opposite is 20 degrees, so T2 over sine 20 degrees equals, and we use the same one again, 98.1 divided by sine 100 degrees, rearrange. This time you get T2 equals 98.1 sine 20 degrees divided by sine 100 degrees. And to 3 significant figures, 34.1. Yeah? Okay, so that one's not too bad using triangle of forces and the sine rule in this case, yeah? But what happens if, like Liam said, we want to do it resolving vertically and horizontally and we end up with some simultaneous equations? So let's have a go at that just to see the difference. And let's see if we can get the same answer, because now we know what we're trying to get. So we know it's in equilibrium, so we know that the sum of the horizontal forces is 0 and the sum of the vertical forces is 0. Okay, so let's resolve forces horizontally. So if we resolve horizontally, what have we got? We've got left equals right. Yeah? So what can we say? There are 3 forces. Let's draw the... Okay, if that's 30 degrees up there, that's 30 degrees there. And if that's 70 up there, that's 70 there, because of alternate angles on parallel lines. Yeah? Right, so what is the component of T1 horizontally? So remember I said when you know it to the horizontal, it's the angle to the horizontal, it's times the cosine of the angle. So we can say T1 cosine 70 equals the horizontal component of T2 acting to the right. So that's T2 cos 30. Yeah? Now we can't solve that because there's two unknowns in there. We don't know either T1 or T2. So we can't solve that yet. So let's leave that for now and let's have a look if we resolve vertically. So if we resolve vertically, up must equal down. So what's acting vertically? We've got the vertical component of T1 and the vertical component of T2 acting up. So that we can say T1 sine 70 degrees plus T2 sine 30 degrees equals the vertical force down, which is 98.1. Okay, so now we've got two equations with two unknowns. We can solve them using simultaneous equations. Yeah? So how are we going to do that? What can we do to make sure we get the right answer? Not quite. Remember when you did simultaneous equations on the algebra block course, we can either do it by elimination or by substitution. Yeah? So in this one, it's probably easier to do it substitution because we've got sines and cosines in there. But what can I say T1 equals? T1 is going to equal T2 cos 30 degrees divided by cos 70. Yeah? So then we can replace T1 in this with that one. So we can say T1, so instead of T1 we write T2 cos 30 degrees over cos 70 degrees plus T2 sine 30 degrees equals 98.1. We can then, if we want to solve for T2, we've got to factorise it. So we can have T2 outside the bracket, and then we've got cos 30 over cos 70 plus sine 30 degrees equals 98.1. And then we can divide by this. So T2 is going to equal 98.1 divided by all of that. Cos 30 degrees over cos 70 degrees plus sine 30 degrees. And we should be able to do that on our calculator and get the same answer. Yeah? Hmm? Sorry? Yeah. Which isn't quite what we got before, is it? Anyone think why there's a difference? Possibly. Have I done it right? That's the question. Exactly. I agree with you there, Fitz. But can anyone see, have I made a mistake in there? That's one of the things is, if you get the wrong answer, you go back and see, have I made a mistake somewhere? T1 cos 70 equals T2 cos 30. That's right. So T1 is going to be T2 cos 30 over cos 70. Up equals down. We've got T1 sine 70 plus T2 sine 30 equals 98.1. Substitute in. I can see where I've made a mistake. Okay. No, it's not that I've made a mistake. I can actually see where I've made a mistake. Okay? Here this says T1 sine 70, yeah? And then T1 is T2 cos 30 over cos 70. I forgot the sine 70. Yeah? T1 sine 70 and T2 cos 30 over cos 70 is just T1. So I forgot sine 70 degrees there. Well, you could sine 70 degrees, I missed there. No, you don't. You just do it like that, but I just forgot one. So it should work now. Which is why, as Fitz said, simple is easy. If you do it this way, you can get to the answer, but it's a bit of a pain. So let's just make sure that it does give the right answer. It does, yeah. So that does give the right answer. So be careful when you do it this way. Go for the simple way. Right. Okay, so I made a big error in there because I forgot the sine 70. But then it works, and if you're going to get the right answer now, 34.1.
Oh, is it sine 70 on the top?
Yeah, cos 30 times sine 70 over cos 70 plus sine 30, yeah.
Oh, I see.
Yeah. And then, probably, yeah. And then once you've got T2, you just do T2 times cos 30 divided by cos 70, and you get T1, and you will get the same answer. It's just, the pressure of being videoed, I mucked up. I'm going to look great on there. But as I said to the group this morning, it's good that I'm not perfect. As my mum used to say, you used to be conceited, but now you're just perfect. Big-headed. She was taking the mickey. Okay, so we need to be able to, it is simpler to do the triangle of forces and use the sine rule or the cosine rule. Some people are not happy using the sine rule or the cosine rule, and then you have to resolve horizontally and vertically. But if you're comfortable with the other way, let's go that way. And I think we'll just finish with one more question and then see if we can do it. Yep, Nick?
Just really quickly, sorry, mate. Can you show me where I should have my brackets on this calculator? Because I'm using it for those answers.
Okay, we'll just finish this and then I'll show you after, yeah? because we're just going to finish with one more question and see if you can talk me through it. Okay, so we've got a mass of 20 kilograms is supported by a cord which passes over a frictionless pulley B, which you'll see in the diagram, and is fixed to the wall at C. So here's our diagram. We've got a wall, ceiling up here, there's our pulley, P, there's our 20 kilogram mass, and then we've got the pulley connecting it to the wall. So questions we want to answer is find the magnitude of the force in the cord, first, and secondly, find the magnitude and direction of the reaction at the pulley. Okay. Oh, I think I'll switch to a different colour. Oh. Yeah, that one died. That was brand new this morning. Thank you. Right, so there's the problem we're trying to do, and we're going to use a triangle of forces to do it rather than resolving. So, first one is quite straightforward. Okay, what's the force acting down on that side of the pulley? Yeah, 20G, yeah? So that's 20G, so that's 20 times 9.81, which is 196.2, yeah? So that's 196.2 newtons, okay? Now, is the weight moving down? Is the pulley moving? So what's the magnitude of the force in the cord got to be? 196.2, yeah, because it's not moving. So if it's trying to go down there using that force. Yeah. Yep, sorry, we'll put C there, yeah, C. Yeah. So if the tension in the cord this side, due to the weight, is that the tension in the other one must be the same. Okay, so we know that. So now we know that, so now we can actually look at doing the free body diagram and then a triangle of forces. So what's it going to look like? So let's quickly draw it again and just work out what we've got. What's our free body diagram going to look like? So yeah, so at the moment, all we're going to have is we're going to have our weight acting down and our force in the, so yeah, so it's going to be like that. Yeah? Well, that's the free body diagram we've got. That's our 196.2 down there and 196.2 there. Yeah? So there's our pulley there. So that's our free body diagram. That's not our triangular forces. Yeah? So we've got that. Do we know any angles? Actually, we do. But I forgot to draw it on the diagram, which doesn't help, does it? We know that that in there is 60 degrees. Makes it a bit easier when you know the angle, doesn't it? So I know that that's 60 degrees. Okay? That's our free body diagram. Now we need to draw, now we need to draw our triangular forces. Yeah? So what we're going to get we're going to have that one acting down there, and then so that's 196.2 newtons. Like that, and so our resultant of those two forces is going to be that. So there's our resultant. Okay? And what's the angle in here? If that's 60, there, that's got to be 120. Good, yeah. Okay? So we can do that. We can draw our diagram to get our resultant force. Yeah? I think we are going to use the cosine rule, yeah. So let's just call that F, resultant force.
There's 120 on the inside.
Yeah, inside. There's this angle in here. Yep.
Oh, okay, so that's 60 and 60.
Because if that's, by our diagram here, this one out here is 60.
Oh, okay.
So that one must be 120 to make it up to 180.
Oh, okay.
Yep. So now we've got our triangle, we can work out what the resultant of those two forces are. Yeah? So we're going to use our cosine rule to do it. So the resultant force, so what's F going to be? We can say, we're using the cosine rule. So F squared is going to equal 196.2 squared plus 196.2 squared again minus 2 times 196.2 times 196.2 times cosine of 120 degrees. Okay. So 196.2 squared plus 196.2 squared again, minus 2 times 196.2 times 196.2 times cosine 120, and then square root that. And I get 339.828, whatever, so we're going to round that to 340. Yeah? Yep. So 340 newtons, and that's the three significant figures. So now we worked out the resultant force. Is that what they're asking us? No. Because what we're going to have, if you think about it, is on our pulley system, we've got those two forces acting like that, which gives our resultant, but then there'll be the reaction to that, which puts it in equilibrium because our pulley's not moving away, it's not flying off the wall. So that's the result. Now we've got that. So now what we've got is, if you think about it, on our pulley, let's draw it over here. Here's our pulley, and we've got our force acting there like that, and there are two forces acting there, which give a resultant of, if you look at this, it's acting down here. There's our resultant. Yeah? So that's our resultant force. That's that F we just calculated. And the reaction force is equal and opposite to that. Okay? So we now know the magnitude of our reaction force. It must be 340. But how are we going to? It's in the opposite direction. So how are we going to do that? We need to work out an angle. So I can work out this angle here. Yeah. And then remember our R is that way. Mm-hmm. Yeah. Why is it 30 degrees? Why do we not have to use a cosine rule or sine rule? Yeah, because what type of triangle is this? It's an isosceles triangle. So if that's 120, the other two have to add up to 60. Yeah? And they're equal. So that must be 30 degrees in there. So if that's 30 degrees in there, that's 30 degrees there. Hmm. Yeah. So, but we can do that. So the reaction is, so our reaction here, we found out that one, and then so the reaction has a magnitude of 340 newtons acting 30 degrees to the right of vertical. Okay? So we can work out, if they weren't the same, yeah? If this was a different example where these two forces were not the same, obviously you could use the sine rule to work out that angle and then and then the other one is equal and opposite, yeah?